This week we're going to be working on setting up volume integrals. The hardest part is figuring out the inequalities that will become the bounds to describe a region. So we're going to start off with kind of baby steps. We have here an iterated integral that describes a 3D region, and we want to look at what region the bounds describe, and then when it comes time for us to take a region and describe it with bounds, we'll have some idea about how these things are put together. So just like with integrals over 2D planar regions, the bounds go with the particular variables, and we can read off inequalities that describe the region. So looking at the innermost variable z, the bounds on z look like they are z goes between x squared plus 3y squared and 44 minus x squared minus y squared. Then the bounds on the next variable out x are from 0 to 3y, and the bounds on y are from 0 to the square root of 2. So if this was just a 2D planar region, then we would just have bounds on x and y. So we can get a feel for this by drawing this graph in the xy plane. We have y between two horizontal lines. Y equals 0 would be the x-axis here, and y equals root 2 would be a horizontal line. And then x goes between 0 and 3y. So x equal 3y would be y equals 1/3 x, so it's a line with slope 1/3 coming up here. And of course x equals 0 is the y-axis. So if these were the only bounds that we had, we would have this triangular region. But we're actually in 3 dimensions, so there's a z-axis. So we can visualize our triangular region here, and in the you could sketch it here in the xy plane, like that. And then what we have are these two surfaces. Each surface, the top surface, the high values for z, would be this elliptic paraboloid. It's an elliptic paraboloid that when x and y are both 0, it's up here at 44, and then it starts curving down, right, sort of uniformly in the x and y directions. Then we have this other surface, z equals x squared plus 3y squared. This one, when x and y are both 0, so at the origin z is 0, and then these move up parabolically. If you freeze y, then x will move up like this, and if you freeze x, y will move up, but a little faster because of the coefficient 3 on the y squared. So we have something like a bowl opening up and kind of an elongated bowl, or an elongated bowl opening up and a sort of uniform bowl opening down. And we just want the part that is cut out by where x and y would be hovering over this triangular region. So we would see this line here would make a line like this on this surface, and the line moving up on the lower surface, and then this line would become a line moving down and a line moving up on that surface. So we have kind of a parabolic region that has this cross section, or its shadow in the xy plane is a triangle. It might be easier to visualize this if we take our inequalities and we graph this using Plot 3D and Mathematica. So that's what I've done. I've got Mathematica open here, and the command to plot surfaces is Plot 3D. So I'm going to plot both of those elliptic paraboloids, and I use the bounds on y. I'm plotting y from 0 to square root of 2, and then once Mathematica knows what y is doing, then the x value just goes from 0 to 3 times y. So then I could just show that plot, and it looks like I didn't express the output. You can sort of see our elliptic paraboloids opening up and opening down, and coming together right at this point in the middle. Let's look at another example. Here's another triple integral. We can just read off the bounds. Z is going from 0 to 2x plus y plus 4. So z is trapped between the xy plane and some other plane here. X is trapped between negative square root of 4 minus y squared and the square root of 4 minus y squared. and y is between two constants, 0 and 2. We can start just looking at this in the xy plane, ignoring z for a minute. So y is between two horizontal lines, right? Y equals 0 is the x-axis, and y equal 2 is a horizontal line up here. And if we look at either end, we have either x is the negative square root of 4 minus y squared, or x is the positive square root of 4 minus y squared. If we square both sides, we get x squared either way. When we square both sides, if there's a negative, it'll go away, but we'll have x squared equals 4 minus y squared, so x squared plus y squared equals 4. So what we have are the parts of the two sides are really two parts of a circle of radius 2. So this region just in the xy plane is a semicircle, right? Or a filled-in semicircle. That's what these two inequalities describe. Now, if z was free, we would basically get kind of an infinitely long half a carrot stick here. So this is the x-axis, this is the y-axis, and this is the z-axis. And if z was free, we could just go up as high as we wanted, or down as low as we wanted in z, so if there was no constraint on z. And it would just be sort of an infinite half filled in cylinder here. But there are bounds on z. The lower bound on z is that z equals 0, which is the xy plane. So you don't see anything below the xy plane. We just cut that part off. And then above the xy plane, we're cutting it with a plane. It's got slope 1 in the y direction and slope 2 in the x direction. So this plane is kind of sloped up with slope 2 in the x direction, something like this. And it's also sort of tilted up in the y direction. So it kind of slopes up this way in the y direction. So you can imagine we have a carrot stick. We cut it sort of square on the one side, and on the other side we cut it down like this, and we got a shape that went something like that before our volume. You can get a better picture of it again if we go to Mathematica. So let's switch over to Mathematica, and I'll use the plot 3D command again to plot my two surfaces. So we're going to plot the surface z equals 0 and the surface z equals 2x plus y plus 4. And we said the bounds on y went from 0 to 2, and bounds on x is running from the negative square root of 4 minus x squared to the positive square root of 4 minus x squared. Let's see. Oh, sorry. I made a mistake. That's supposed to be y. So there we go. Okay, and you can see the two surfaces. So looking down on it, there's the region that's described in the xy plane, and then we just have those two surfaces, z equals 0 and z equals 2x plus y plus 4, looking like this. So there's our shape.